All right, thus far in this course, we have gone in one direction only. Given a function, we have found its derivative. That is the derivative of some function f of x equals f prime of x. That's what we've been given. That's what we needed to find. Today, we're going to turn that around. And the notation for what we're going to do today, called anti-differentiation, that is, we're going to be finding antiderivatives, is this. The general antiderivative or indefinite integral of some function f of x. The x here represents the variable of integration, just as in this notation, the x represents the variable of differentiation. The indefinite integral of f of x with respect to x is capital F plus c. The capital F is the antiderivative. This is equivalent to saying the derivative of capital F is f of x. The antiderivative here is capital F. The derivative of f of capital F is small f. Okay. There is something different here, something that has no analogy in differentiation, this plus c. Derivatives are unique. For any given function, there is one derivative. Antiderivatives are not. There are an infinite number of antiderivatives of this function. They differ only by a constant, c. Now let me explain before you start to feel confused. We know that the derivative of x squared is 2x. X squared has only one derivative, 2x. But 2x has an infinite number of antiderivatives. The derivative of x squared plus 1 is 2x. The derivative of x squared minus 3 is 2x. Hence the plus c. Right? That f of x plus c, capital F of x plus c, represents a family of functions, all of which have the derivative f of x. So, if f of x equals 2x, again, the way we would write this is to say the antiderivative, the general antiderivative, note, the general antiderivative of 2x with respect to x is x squared plus c. That family. If we were to graph that family, we would have an infinite number of parabolas. Now, we remember from at the very beginning of the semester what happens when we add a constant to a function. It represents a vertical shift or vertical translation. We would have an infinite number of these parabolas differing only in their vertical orientation. There would be no change in shape. So, with the general antiderivative or indefinite integral, always include the plus c unless you are told specifically that you do not have to, or you're assuming that c equals 0. And sometimes you'll see that on the My Math Lab homework assignments. Okay, now, there is one group of functions for which we have a ready rule for antidifferentiation, and those are power functions. Now, you may remember the power rule for differentiation. The derivative of x to the n. equals n times x to the n minus 1. If we had to break down what we just did, we might say, well, step 1 was multiply by, well, I'll call it the old exponent. And step 2 is to decrease the exponent by 1. And that's exactly what we did. We had the old exponent here, multiplied by it, then decreased by 1 to get a new exponent. That's the power rule for differentiation. Well, as you might imagine, the power rule for anti-differentiation turns that on its head, right? The antiderivative of x to the n with respect to x equals you will note here that the first step in anti-differentiation for a power function is the exact opposite of the second step for differentiation. We increased the exponent by 1. The second step is the opposite of the first step in differentiation. We divide by, I'll call it, the new exponent. Now, of course, in anti-differentiation, there is a third step that has no analog in differentiation, that is the plus c. So for power functions, and remember, they may not be written as power functions. The square root of x can be written as a power function. 1 over x can be written as a power function. So as long as it can be written as a power function, with the exception of 1 over x itself, then we can employ the power rule for anti-differentiation. For other function types, we need to literally know our derivatives backwards and forwards. We have to recognize patterns. And we may also need to watch for multiples arising or disappearing, which are brought about by the chain rule. We have to account for that when we're anti-differentiating. In essence, as a colleague of mine once called it, it is a game of guess and check, but our guesses are educated, okay? So for example, well, let's just try some antiderivatives here. All right, this is a straightforward power function. There's our n. Our antiderivative, x to the n plus 1, divide by n plus 1 plus c. All right, now, for this, I have always told my classes that there are some derivatives that you should know. Okay. You should know that the derivative of the square root of x is 1 over 2 times the square root of x. So what we have here is 2 times the derivative of the square root of x. So we would expect that our antiderivative is 2 times the square root of x. But if you don't feel comfortable with that, remember, this can be written as a power function. What we have here is the antiderivative of x to the negative 1/2. So we can add 1. Dividing by 1/2 is the same as multiplying by 2. Equals 2 times the square root of x plus c. Now, something that you should do in the early stages of anti-differentiation, every time you anti-differentiate, when you find what you believe is the answer, you should differentiate it to make sure that you get back to what we call the integrand here. This is the integral sign, that is the integrand, that is the variable of integration. Later on, when we're doing definite integrals, you'll see the limits of integration here. The indefinite integral, the general antiderivative, is a function or family of functions. The definite integral, which we shall see later, is a number. Okay. When you have something like this, you have the sign of u there. You know that there is a function whose derivative is sine, or technically negative sign. You know that your antiderivative has to have in it a cosine of u being 2x. If you were to differentiate that, you would get, by the chain rule, negative sine 2x times 2. There is no negative here. We have to supply. There's a 2 missing. So we have to undo the chain rule in essence. Now, if we differentiate this, we get negative 1/2 times negative sine 2x times 2. The negatives cancel, the 1/2 times 2 yields a positive 1. There's our antiderivative. All right? Watch for that. Always, always check. Remember, the game is guess and check. The educated part of the guess comes from knowing your derivative rules. And very similarly, here we have the cosine of x over 2, or 1/2 x. Well, we know that that has to include the sine. And the u, the argument, does not change. So we know that our antiderivative has to include that. If we were to differentiate that, we would get the cosine of x over 2 times 1/2. Don't have a 1/2 here. We have to undo that chain. Now our derivative is 2 times the cosine of x over 2 times 1/2, 2 times 1/2. Very similarly, you know that the derivative of e to the u is e to the u du dx. So again, you know that your antiderivative has to include e to the u. If you were to differentiate that, you would find that your derivative is e to the negative 3x times negative 3. We have neither the negative nor the 3. Again, we have to account for the chain rule. And for the fact that this is a family of functions. Again, our derivative, negative 1/3 times e to the negative 3x times negative 3. Negative 1/3 times negative 3 is 1. And finally, one more that I hope you'll recognize right away. I hope you will see that when you have a constant over this, you're dealing with an inverse sign or arc sign. If this had said 1 over the square root of 1 minus x squared, our antiderivative would simply be arc sine x. But it says 2. Well, with antiderivatives, you can pull out a constant multiple. So the antiderivative of 2 over the square root of 1 minus x squared is 2 times the antiderivative of 1. And what do we have here? We have 2 inverse sine or arc sine x plus c. Now later, we'll get into substitution, or U substitution as it is sometimes called, wherein we're going to have to deal with more than just constants. But that's for another day.